Okay, now that we've seen how to solve one non-standard maximization problem with two variables, and we could compare it to a graphical approach, let's look at solving non-standard maximization problems with more than two variables. So we'll start with this maximization problem. Remember, the first main step, or the first key step, is to get all less than equal to constraints. So we need to change this greater than equal to 24 constraint. Simply multiply both sides by -1, giving us -2x minus y minus z less than equal to -24. Once we've done that, we're now ready to fill in the initial tableau. The first constraint, 1x, 1y, 2z, plus our slack variable equals 38. Yes, I am skipping over the step of writing out the equations. Our second constraint, we'll use the less than equal to form. -2x minus 1y minus 1z, no s1s, plus s2 equals -24. And the objective function, everything over to the same side as p on the bottom. -3x, -2y, -2z, no slacks, and again, I am leaving out the p column. Alright, we do have a negative constant. So we go find the most negative number to the left of that negative constant in the same row. So -2, that'll give us our pivot column. We'll go ahead and do our ratio test as before. 38 over 1 is 38. -24 over -2 is 12. And since we're non-standard, we do pick the smallest positive ratio. That will be right here. So we're going to pivot on the entry in row 2, column 1. Doing so provides our second tableau that we see here. We'll notice there are no negative constants. No negative constants. That means we are in the feasible region, and that we will proceed with a standard simplex. Proceed with a standard simplex. Alright, to do the standard simplex, we look for our pivot column by choosing the most negative number in the bottom row. Most negative number in the bottom row, -3/2. That'll give us our pivot column. We'll do our ratio test. But keeping in mind, since we are standard simplex, we're not going to pivot on a negative entry. So we really don't even need a ratio test. We only have one possible entry to pivot on. The entry in row 1, column 5. So we'll pivot on the entry in row 1, column 5, and get the resulting tableau we see here at the bottom. We see there's no negatives in the bottom row. And since we were doing standard simplex, this is a final tableau. No negatives in the bottom row, no negative constants. This is a final tableau, which means we can now provide the optimal value and the optimal solution. The optimal value, the max P, is 114. And the optimal solution, remember our main variables for this problem are x, y, z. X is active in the second row, so x is 38. Y and z are both inactive and therefore equal to 0. If we check this in our objective function, 3 times 38 is indeed 114 plus 0 plus 0. So P does equal 114 at this point. So there's our maximum value of P. Continuing on, we have a problem at the top of page 4. So, maximizing this problem, note there are just two variables, so you could do this one graphically if you wanted, but we'll go through the algebraic approach and I will let you check this on your own graphically if you wish. So before we create our initial tableau, we do need all the constraints to be less than equal to. So negative y less than equal to negative 10, negative 2x plus y less than equal to 0. So we're ready to write in our initial tableau. We've got the main variables x and y, 3 constraints that will be turned into equations, so 3 slack variables, and then our constant column. Alright, filling in the initial tableau, the first constraint's already less than equal to 1, 1, first slack variable, 25. Second constraint, no x's, negative 1y, slack variable 2, and negative 10. Third constraint, we're using the less than equal to form, negative 2, positive y, no slack 1, no slack 2, 1 slack 3, less than equal to 0. And the bottom row is reserved for the objective function, so negative x minus 2y, no slacks, p is equal to 0. Alright, we do indeed have a negative constant. Find the most negative number to the left of that negative constant. In this case, there's only one, so that will be our pivot column. We'll do our ratio test just as before. 25 over 1 is 25. Negative 10 over negative 1 is 10. 0 over 1 is 0. Now remember, we're in the non-standard phase, so we do choose the smallest positive ratio. The smallest positive ratio, 10. So this will be our pivot entry. It's negative 1. So we pivot on that entry, and we do indeed get the second tableau. We label our active variables. Again, it's not something you typically have to do. This is for the sake of your notes. Y is active in row 2. S1 is active in row 1. S3 is active in row 3. Our basic solution, of course, we have S1 equaling 15, Y equaling 10, S3 equaling negative 10. Of course, X is 0. It's inactive. But note, we do have a negative constant. Yes, we do. So we are not in the feasible region. So we're going to repeat those steps until we get into the feasible region. We still have our negative constant. Find the most negative number to the left. That's the most negative number in that row. We only have one, so that'll be our pivot column. We'll do our ratio test. 15 over 1 is 15. We can't divide by 0. Negative 10 divided by negative 2 is 5. Smallest positive ratio. So we pivot there on that negative 2. Pivoting there produces the third tableau. Again, the active variables, x is active in row 3, y is active in row 2, S1 is active in row 1. Our current basic solution, x is 5, y is 10, S1 is 10. Any rows with a negative constant, No. So that means we are in the feasible region. Remember, once we get to the feasible region, we pivot as if it's a standard max problem, way back like we did in 4.1. So, do we have any negative numbers in the bottom row? Yes, we do. The most negative gives us our pivot column. Now, remember, since we are in a standard process, we are in the feasible region now. We cannot pivot on negative ratios, really leaving us only one entry to pivot on. Row 1, column 4. So pivoting on the entry in row 1, column 4, we get this fourth tableau. You'll notice no negatives, and also no negative constants. So we are at the final tableau. We can now give the optimal value and optimal solution. Okay, labeling the active variables as the notes are asking us to do. S2 is active in row 1, Y is active in row 2, X is active in row 3. Are we finished yet? Yes. Okay. So our optimal value max P 125 over 3, and it occurs at the optimal solution X, Y equals X is 25 over 3, Y is 50 over 3. And there we have solved a third non-standard maximization problem. One in the first introductory video, and now two in this video. Let me know if you have questions. Thank you.